Hello everyone. In the last class we were discussing about the in fact we solved a problem related to the mixed design of PQC and we solved the problem for the design flexural strength. So, as I mentioned that today also we will solve two problems. The first problem will be similar to what we have done in the last class, but today we will try to see the solution corresponding to the design compressive strength, and we will also solve a problem to produce a high strength concrete mix. So, let me first write down the problem here. What are the inputs given in the design problem. So, we have to design a M40 concrete here, alright. The type of cement which we are using is OPC 43. The nominal maximum aggregate size is different in this case. So, the nominal maximum aggregate size is 19 mm. Minimum cement content and the maximum water cement ratio criteria remains the same. The workability to be achieved is similar to what we have used in the last case, 25 plus minus 5 mm. The type of aggregate is again crushed angular, and here also we are using a super plasticizer. So, now the specific gravity of the individual material is similar to what we have used in the last example. So, for cement the specific gravity is 3.15, for coarse aggregate it is 2.74, for fine aggregate it is 2.62. Okay. Water absorption, let us take similar water absorption, but we will change the free moisture present in the surface. So, water absorption for coarse aggregate is given to be 0.5% and for fine aggregate it is given to be 1%, and free moisture is present in this problem. Coarse aggregate it is 0% free moisture, but in fine aggregate we have 4% free moisture. So, therefore, the total moisture content in fine aggregate becomes equal to 4 plus 1, that is 5%, out of which 4% is in the surface and 1% is corresponding to the water absorption. Here also we are using zone 2 sand. So, let us now try to, with this inputs we can start solving the problem, start completing the mixed design, and we will use similar steps what we have seen in the last class. So, the first step is to calculate the target strength, alright. So, for the target strength here also we have two formulas. So, the first formula is that F dash Ck is equal to F Ck plus 1.65 into SC, and again F dash Ck is equal to F Ck plus x. Here the value of x is a function of the grade of the concrete. In our case it is M40, so the value is 6.5. So, F dash Ck becomes equal to 40 plus 6.5, which is 46.5 MPa, and in this formula we have to know the value of SC. So, if you see here the value of SC for M40 is equal to 5. So, we will use this value here. So, this becomes equal to F dash Ck is 40 plus 1.65 into 5. So, this becomes equal to 48.25 MPa. So, out of these two values 48.25 is maximum. So, the target compressive strength is equal to 48.25 MPa. Okay. So, this is what we will consider in the design, 48.25. In the second step what we will do, we will see the amount of entrapped air. So, entrapped air is a function of the nominal maximum aggregate size which you see here. So, it is 1%. So, percentage of entrapped air is equal to 1 by 100 into 1. So, this is 0.01 meter cube. Okay. So, and this we will use at the end when we are calculating the proportion by volume, or we are calculating the total volume or of the concrete. So, this is the second step. Then we will go to the third step of selecting the water cement ratio. All right. So, water cement ratio is a function of the target compressive strength and the grade of the cement. Our target compressive strength is equal to 48.25. So, it is somewhere between 48 and 53, and which means the water cement ratio we have to interpolate between 0.36 and 0.33. So, since our target grade is 48.25, it is very similar, very close to 48. So, let us not do any interpolation here, rather take the direct value. So, we can take the water cement ratio to be approximately 0.36. If you remember, we have to apply a check here. So, this 0.36 is less than 0.4. So, it is fine, we can proceed to the next step. In the next step, we have to select the water content. Again, we have a suggestive table corresponding to the NMAS. So, the nominal maximum aggregate size is 19. So, the suggestive water content is 186 kg per meter cube, but this has some conditions. For example, this is for a slump of 50 mm, all right, and this is without any admixture. So, similar to what we did in the last problem, our design slump is 25. So, we have to reduce 3%. Okay. Today I am doing the calculation, the speed of doing the calculation is more, considering that we have already completed this discussion in the last class. So, it will be easy for you to follow this particular lecture. So, this is 180.4 kgs per meter cube corresponding to 25 mm slump, and corresponding to the admixture we are using superplasticizer. So, 20% reduction in further in this particular water content. So, 180.4 into 0.8. So, this becomes equal to approximately 144 kg. Okay. So, 144 kg is the amount of water which we have to take. So, now we know the water cement ratio, now we know the water content. So, WC ratio is 0.36, water content is 144, just put it here to get the cement content, which is equal to 144 divided by 0.36, which is equal to 400. Same value which we got the last time. Again we will apply two checks here. The minimum is 360, so it satisfies the minimum criteria. The maximum is 450, it satisfies this criteria also. So, we are good to go ahead, all right. Now, the next step is to take the proportion of the coarse aggregate. We are here, we are here. So, our value will be 0.62, all right. So, the amount of coarse aggregate that we have to use is equal to 0.62, but the condition here is again related to the required water cement ratio of 0.5, all right. So, we have to do the adjustment. Now, how to do the adjustment? We know that for every decrease in water cement ratio by 0.05, we have to increase this value. So, for every decrease in the water cement ratio by 0.05, we have to increase the volume by 0.01 meter cube. Okay. So, that is what we are going to do here also. So, this will be equal to 0.62 plus 0.5 minus 0.36 divided by 0.05 into 0.01. Okay. So, if we do this calculation, you get the value as 0.648, which means 64.8% by the volume of total aggregate will be coarse aggregate. So, therefore, fine aggregate becomes equal to 1 minus 0.648, which is equal to 0.352. Okay. per unit volume of total aggregate. So, this is the proportion which we have got. Now, the next step is checking the gradation. So, that we have to ensure that for the given coarse aggregate blend and the zone 2 fine aggregate which we are using, we are able to reach the combined gradation which we have already discussed in the last class. And then finally, we will have the proportions with us. So, let me write down the proportion. Now, in this problem the absolute volume of concrete becomes equal to 1 minus 0.01, all right. So, this is 0.99 meter cube. Then we have cement, we know the specific gravity, we know the mass. So, we can calculate the volume which will be equal to 0.127. Then similarly, we can calculate the volume of water, weight of water was given, specific gravity we know, this becomes equal to 0.144 meter cube. Then we have superplasticizer, let us say we are using at the rate of 1% by weight of cement. So, this becomes equal to 0.01 multiplied by 400, this is the weight, and then we have to divide by the specific gravity 1.2 into 1 by 1000, this becomes equal to 0.003 meter cube. Now, we have all the proportions. So, the volume of all in aggregate becomes equal to 0.99 minus the summation of all the other volumes, all right. So, this becomes equal to 0.716 meter cube. Okay. Now, a part of this volume will be occupied by the coarse aggregate. So, 64.8% of this volume belongs to the coarse aggregate, whereas 35.2% of this volume belongs to the fine aggregate. So, now we have to calculate the weight of the coarse aggregate and fine aggregate using these proportions, because we know the specific gravity of coarse aggregate and fine aggregate. So, the weight of coarse aggregate becomes equal to 0.716, 64.8% of this volume 0.648, specific gravity is 2.74 into 1000. So, in kgs per meter cube this becomes equal to 1271 kg per meter cube. So, fine aggregate becomes equal to again 0.716 into 0.352 into 2.62 into 1000. So, this becomes equal to 660.3, or let us say 660 kgs per meter cube. Okay. So, now we have all the mixed proportion. Again this is by SSD. If I want to do it in dry condition, then I have to know the water absorption and the presence of free moisture also. In case of coarse aggregate, we did not have any free moisture, but the water absorption is 0.5%. So, similar to what we did in the last class, that now the changed value of coarse aggregate will be 1271 divided by 1 plus 0.5 by 100, all right. So, this becomes equal to 1265 kgs per meter cube, all right. Now, in case of fine aggregate, we have two cases, one is the water absorption and the other is the presence of free moisture. Remember, this was in SSD condition, and in this condition we have not considered the presence of free moisture, all right. We have only considered the presence of the absorbed moisture in the fine aggregate. So, first let us find out the dry mass of the fine aggregate corresponding to the water absorption. So, this becomes equal to 660, which we have got, divided by 1 plus 1 by 100, all right. So, this is equal to 653 kgs per meter cube. Now, this is the dry mass, and now we have to calculate the free surface moisture corresponding to this particular dry mass. So, if I want to find out, let us say, the total weight or total, you can say, yes, weight of fine aggregate in wet condition. When I say wet condition, it includes, let us say, if this is the aggregate. So, we have some absorbed water and then we have some surface water. So, total weight in wet condition should include both the surface water and the absorbed water. So, in that case it will be equal to the total moisture, which is equal to 1% which is inside the pores plus 4% which is on the surface. So, 5%. So, if I want to calculate the total weight, it will be equal to 653, the dry weight, divided by 1 plus total moisture, which is 5 divided by 100, alright. So, this value will be equal to 686 kg per meter cube, alright. And therefore, what is the weight of surface moisture? Surface moisture is equal to the wet aggregate minus the SSD aggregate, is not it? Because this total wet aggregate minus the SSD aggregate will give me the value of the total surface moisture. So, the wet aggregate is equal to 686, SSD aggregate is equal to 660 here from here, and this becomes equal to 26 kgs per meter cube, alright. So, this we have to again adjust in the total water content. Now, therefore, the changed water content will become equal to, earlier it was 144 in SSD condition that we calculated, this is 144, which means we have to subtract the amount of free moisture from here, which we are already considering, because you see this free moisture is the one which will facilitate workability also, which means this is active water which also reacts with cement and which is also available for workability. But the water which is inside the pores, they are not available, which means in the SSD condition whatever we calculated, which was you see 144 kgs per meter cube, this value. So, this we calculated considering the presence of surface moisture, alright. But again we have some surface moisture in the fine aggregate, which means this water content ideally should be reduced, because this is the extra water which we are adding, but already in the fine aggregate we have some presence of free moisture which we need to adjust in this particular water content. So, for the presence of free moisture we have to first subtract 26, alright, this we will do, and then we have to add the additional amount of moisture which is present. What is that additional amount of moisture which is present? It is equal to 1271 in the coarse aggregate minus what we got here 1265, alright. So, this is equal to 6. So, this 6 we have to again add here, okay, because that we have not considered in our calculation, alright. The moisture which we have to add becomes equal to 124 kgs per meter cube, okay. Similarly, once we have calculated, the water cement ratio can be worked out for the given cement content. So, since we have now discussed the calculation of the proportion of different ingredients or materials that are used to produce the concrete, the other steps are similar to what we have discussed. For example, the next step will be that for these calculated proportions we will have to make trial samples, and for those trial samples we have to ensure that the required slump criteria and the required durability criteria is satisfied. If they are not satisfied, we can make some adjustments in the proportions, and if they do satisfy, we will proceed to make further trial samples. Now, the further trial samples will be made considering the calculated water cement ratio and plus minus 10% water cement ratio, and then we will plot the graph between water cement ratio and the compressive strength or the compressive strength of the concrete. We will draw the graph, we know what is the target strength, corresponding to the target strength what is the design water cement ratio, we will estimate the same, alright, and this completes the mixed design process as well. We will stop here today, and we have discussed or we have solved a problem which is related to the mixed design of PQC based on compressive strength, and by this we have also completed our discussion on the mixed design of concrete in general that we use in pavement construction. And in the next class we will discuss about the mixed design of dry lean concrete mixtures that are typically used just below the concrete slab in a usual usual cross section of concrete pavement that we use in the highways. After that we will also discuss about the mixed design of pervious concrete, which as I mentioned is a special type of concrete, and we will also discuss in general about its application, about the details, and of course the mixed design process. Thank you.